Whether you're a bioprocess engineer hunting for the perfect scaled-down model, a biotech founder architecting the leap to commercialization, or a scientific analyst who craves raw technical truth, you've reached the technical edge. In this space, we live by a single mantra: the process is the product. Welcome to the Biomanufacturing and Fermentation Technology podcast with Prasad Ernala. Hit subscribe and ring the bell to join a global community and stay at the vanguard of biotech translation. Let's build the bioindustrial future together.
In Part 2 of Designing and Running Experiments with AI Assistants, we move from design philosophy to execution discipline, where AI accelerates experimental setup, but biological and engineering constraints still define what is possible. Core signals from Part 2. Optimize responses that truly impact cost, scale-up, and quality. Titer alone is rarely sufficient. Space and time yield, impurity burden, viscosity, oxygen demand, and CQAs often determine commercial viability. Select factors that are mechanistically meaningful and operationally controllable. Define ranges that capture nonlinearity without crossing into oxygen limitation, toxicity, precipitation, or culture failure regimes. Use screening designs to identify major drivers quickly, not to optimize. Be aware of aliasing, curvature blindness, and survivor bias from failed fermentation runs. Shift to response surface designs such as CCD or box behenken when curvature matters. Recognize that biological optima are local and regime dependent, especially when scale changes shift mass transfer realities. Apply Bayesian or adaptive AI-driven designs when experiments are expensive and landscapes are complex. Balance speed against interpretability and regulatory transparency. Treat AI as an execution accelerator. It generates designs, compares efficiencies, and flags constraint violations, but human validation ensures biological realism, safety, and statistical adequacy.
Biology is messy. I mean, that's the fundamental truth we all wake up to every morning, right?
Oh, absolutely.
You've got living cells, enzymes, temperature fluctuations, shear stress. And honestly, sometimes it feels like if you just look at the bioreactor the wrong way, the whole run fails.
It is inherent chaos.
Yeah.
It really is.
Yeah.
And the natural instinct, especially for scientists, is to try and control that chaos by, testing everything.
Every single knob.
Every knob, every lever. But in a biological system, testing everything it's mathematically impossible. You just run out of time, money, substrate.
Long before you run out of variables.
Easy.
Exactly. And that bottleneck brings us right to the core question we're tackling in today's deep dive. We're looking at this really comprehensive set of notes on designing and running experiments with AI assistants. This is lesson 2 in our series, and the mission is super specific.
It's very practical.
How do I go from a messy, undefined biological problem to a clean, efficient experimental plan, a CSV file you can actually load into a reactor?
Right. This isn't just about doing science in some abstract way. It's about operationalizing it. And the source material here proposes this really interesting marriage between the old guard classical design of experiments, or DOE,
right,
and the new guard, which is, AI and large language models.
Okay, I want to be careful with that term DOE, because I know for a lot of people that just triggers trauma from grad school statistics.
Oh, the PTSD is real.
Sweating over p-values and ANOVA tables. But what we're looking at today suggests that before you even touch the math, and definitely before you prompt an AI, you have to do something much more human. You have to define what winning actually looks like.
Which sounds so trivial, right? You just say, I want the experiment to work. But the source material makes this distinction here that I think is the most important takeaway of this whole first section.
Which is?
It warns against optimizing the wrong thing. In bioprocessing, you typically have 3 competing masters: titer, productivity, and quality.
But I'm guessing they rarely get along.
Almost never. Let's break them down. So titer is just concentration. How much stuff is in the tank at the end of the run? Simple.
Okay.
Productivity is a rate. How fast did you make it? And you could have a massive titer, but if it took 3 weeks of tank time to get there, your productivity is garbage.
So you could optimize for a huge yield, but you're losing money because you can't run enough batches per year.
Exactly. You're effectively bankrupting the facility schedule because you're tying up the equipment for too long.
Okay, so that's the first conflict.
And then you throw quality into the mix. And I feel like this is the one that gets ignored in early stage R&D. because it's hard to measure quickly.
Right, because you just want to see a big band on a gel. You want that instant gratification.
You do, but let's say you optimized purely for titer. You blast the cells with high feed rates, you crank the temperature, they pump out a ton of protein. Great.
Sounds good so far.
But because the cells are so stressed, they also dump out proteases, or maybe the protein is misfolded, or the host cell proteins are through the roof. You've created a high-titer soup that is a complete nightmare for the downstream team.
So you won the battle in the bioreactor.
But you lost the war on purification. Precisely. The sources emphasize that your response variables need to be linked to the final product, not just the intermediate step.
So if the AI optimizes a fermentation condition that makes the product unfilterable, the experiment is a failure, no matter what the numbers say.
It's a failure. That's a classic local minimum track.
It's like climbing a small hill and thinking you're at the top of Everest.
Perfect analogy.
Okay, so step 1 is defining a holistic objective. Step 2, then, is looking at the inputs, the factors.
The variables, yeah.
We're talking media components, feed rates, pH, temperature, dissolved oxygen, agitation, the usual suspects.
The whole list.
But there's a phrase in the notes here that just stopped me in my tracks. It says we need to set ranges that are biologically meaningful, not statistically cute.
I laughed when I read that. It's such a perfect description of the problem.
What does statistically cute actually mean?
Well, statistical software, and AI for that matter, it loves symmetry. It loves orthogonality. So if your center point is, say, pH 7, the software will naturally suggest testing pH 5 and pH 9.
Right, a nice even spread.
It looks beautiful on a design chart. It maximizes the statistical variance. It's clean.
But biologically?
Biologically, pH 9 might be a death sentence. It could saponify your lipids or just kill your organism instantly. Or pH 5 might be below the isoelectric point of your protein and it just crashes out of solution.
So the software doesn't know any of that. It just knows the number line.
Exactly. Statistically cute ranges are ranges that satisfy the algorithm's desire for mathematical beauty, but they completely violate the biological reality of the organism.
So this is where the human expertise acts as the boundary condition, the guardrails. You have to look at the plan and just say, no, AI, we are not doing pH 9 today.
It's a risk assessment. The notes explicitly say you have to ask yourself, what could crash the culture? That is your hard limit.
Because you can't learn anything from a dead tank.
Nothing. The math assumes you get a result, even a bad one. Biology doesn't guarantee a result at all.
Okay, so we have our objective, and we've set our boundaries so we don't kill the yeast. Now we get into the actual design, the strategy. The sources break this down into 2 main phases, screening and optimization. Let's start with screening. This is the wide net approach.
Exactly. Imagine you're starting a new process with a new strain. You have, 20 different factors that might matter. Magnesium, trace metals, glucose feed, temperature, impeller speed.
And you genuinely don't know which ones drive the bus.
You have no idea. And you can't test every combination. 20 factors at just 2 levels. That's 2 to the power of 20. That's over 1 million runs.
Yeah, we definitely don't have that many bioreactors.
Not quite.
Yeah.
So the goal of screening is strict filtration. You want to separate the signal from the noise. And the sources point to specific designs for this, like Plackett-Berman or definitive screening designs, usually just called DSD.
Plackett-Berman. It sounds like a law firm.
It really does.
If you've been injured by a bioreactor, call Plackett-Berman.
I like that. But biologically, it's a very clever, very sparse design. It lets you look at a lot of factors with very few runs.
Okay, so what's the trade-off?
The trade-off is resolution. You won't get a detailed map of exactly how everything interacts, but you will get a big red flag waving over the 3 or 4 factors that actually matter.
So it's a coarse filter. You toss everything in, shake it, and see what big rocks are left.
That's a great way to put it.
Yeah.
And the notes warn about a really common pitfall here in fermentation.
Which is?
People often assume linear relationships too early.
Ah, okay.
In screening, you're typically just testing a low point and a high point. You're essentially drawing a straight line between them.
But biology is almost never a straight line.
Never. Enzymes have optimal temperatures, right? You go higher, they work faster up to a point until they denature and stop working entirely. That's a curve.
Right.
If you only test the low point and a toxic high point, you might completely miss the perfect sweet spot right in the middle.
Which leads us perfectly into phase 2, optimization. So once we've used the screening to whittle that list down from 20 factors to maybe the 3 or 4 key drivers, we shift gears. Now we want to find that peak. The notes call this exploring curvature.
This is the shift from what matters to what is the best setting. And to find a peak, you need at least 3 points per factor, a low, a center, and a high. That's what lets you fit a quadratic equation curve.
And the heavy hitters here are Central Composite Designs, or CCD, and Boxbenken.
Right. And the choice between them is actually super practical, which I really appreciate in these notes. A central composite design often requires you to test points outside your original box. They're called star points, or axial points.
Wait, so if I set my high temperature at 37 degrees because I know 38 is risky, the CCD might ask me to run at 39.
Exactly. It needs that to get the mathematical leverage to properly define the curve. But if 37 was your safety limit, well, 39 kills the batch.
So then you're stuck.
In that case, you'd use a Box-Beneken design. It never pushes outside the cube you defined. It's a safer design for biological limits, even if it's slightly less statistically powerful.
That is a crucial distinction for anyone actually trying to run this in a lab.
It's a huge deal.
Now, the sources also mention mixture designs, specifically for media optimization. Why does media get its own special category of math?
Because media is a recipe, and recipes are they're zero-sum games. This is something people often forget. If you have a 1-liter formulation and you decide to increase the glucose solution by 10%, you have to remove 10% of something else.
Usually water.
Right, usually water, to keep the volume at 1 liter.
So the factors aren't independent. I can't just change one without affecting another.
Precisely. In a standard factorial design, the math assumes all your factors are independent. But in media, they're constrained. They have to sum to 100%. If you use a standard design for media optimization, you end up with impossible recipes or varied volumes. Mixture designs handle that constraint mathematically.
It's all so nuanced. You have to pick the right tool for the right phase. But this is where the source material pivots to the really modern stuff. AI-driven DOE. How does AI change this? Is it just doing the math faster, or is it doing it differently?
It's doing it differently. Classical DOE is very rigid. You design 40 runs, you execute all 40 runs, and then you analyze. It's a batch process.
Set in stone.
Totally.
Yeah.
Modern AI, specifically using things like Bayesian optimization, allows for what's called adaptive or sequential DOE.
Adaptive is the key word there.
It is. Think of it like the game hot or cold. Classical DOE is like guessing 20 coordinates on a map before you even start walking. You commit to going to all 20, you measure the elevation at each, and then you draw a map.
You committed to those 20 points before you knew anything.
Right. And adaptive DOE.
Let me guess. It's more like...
It's like taking 3 steps, checking your altimeter, and realizing, oh, the hill is going up over to the left. So your next 3 steps focus in that direction. You update the plan based on the data you just generated.
That sounds objectively better. I mean, you waste fewer runs on dead ends. Why wouldn't we just do that every single time?
Well, there are trade-offs. There are always trade-offs. The notes highlight 3 big ones: speed, interpretability, and validation.
Okay, let's talk about interpretability, because I feel like that's the whole black box problem people worry about with AI.
It is. With a classical central composite design, I can show my boss or a regulator a beautiful 3D surface plot and say, look, here's the interaction between pH and temperature. You can see the curve. It's geometry. It's intuitive.
You can explain it. But with Bayesian optimization...
With Bayesian optimization, the algorithm effectively just says, trust me, the probability of finding the maximum is highest in this region.
So the answer is, the algorithm spoke and I listened.
Right. It's much harder to explain why it worked. You get to the answer faster, but you might understand the underlying biology less.
And that connects to validation, I'm guessing?
It does. If you don't understand the why, it's a lot harder to defend the process if something goes wrong later on.
So it's a balance between pure efficiency, just getting to the high, tighter, fast, and actual scientific understanding.
Exactly. It's a spectrum.
Now, Section 6 of our deep dive gets into the real nitty-gritty. AI in practice. This isn't just theoretical. The sources describe an actual workflow.
And the workflow is surprisingly collaborative. It's not AI replaces the scientist. It's more AI proposes, scientist critiques.
The notes mention using AI to generate run tables that are CSV ready, which I have to say, for anyone who has manually typed experiment settings into equipment software, that is a blessing.
Oh, it's a huge time saver. But the really interesting part is the example prompt they provide in the lesson.
What's the prompt?
It's simple. Generate a screening DOE for 8 media factors in yeast fermentation with realistic ranges.
Straightforward enough.
Sure. And the AI will churn out a beautiful table in seconds. But then comes the most important step, the group critique. The lesson just hammers this point that you cannot just take that table and run with it.
You have to ask.
You have to look at it and ask, what would fail in a real lab?
We're back to the statistically cute problem again.
We are. The AI might suggest adding two ingredients that you know will precipitate when they're mixed, or it might suggest a temperature that yeast can survive, but the equipment can't actually hold consistently.
So the AI can generate the math, but it can't see the physical reality of the lab bench?
Not at all. The validation step is critical. You have to sanity check the machine. The goal is to use the AI to handle the combinatorial complexity, the heavy map of mixing 8 factors, but use the human to handle the biological and the physical constraints.
It's a partnership then. The AI is the navigator, calculating the route.
And the human is the driver who knows the car is about to run out of gas.
Or that the road the GPS picked is actually a river.
Exactly. And that really summarizes the whole outcome of this lesson. It says participants should be able to design a defensible DOE.
Defensible. That's the key word.
It is. You need to be able to stand up and say, we chose this design because we needed to screen these factors. We set these ranges because of these known biological limits. And we use this AI tool to optimize the run list for efficiency.
It's all about intentionality.
Yes. It moves you from just, messing around in the lab to executing a strategy.
So if we look back at the journey we've taken here, it's pretty clear. We started with the chaos of biology.
Utter chaos.
And we realized we need to define clear objectives, first tighter, productivity, quality, and not just optimize for the wrong thing.
Right. And then we select our factors, making sure the ranges are biologically meaningful, not just mathematically pretty.
Then we use screening designs like Plackett-Berman to clear the fog to find what actually matters.
Then we switch to optimization designs to find that curvature, the peak performance. And finally, we overlay this modern AI capability, these Bayesian tools that can learn as we go.
While always keeping that human sanity check in the loop to prevent the whole thing from crashing.
That's the roadmap. It turns an impossible, messy problem into an actual checklist.
It's empowering, honestly. It makes the science feel manageable again.
It does. It lets you focus on the biology rather than getting completely lost in logistics.
Now, before we wrap up, I want to leave you with one final thought. We talked a lot about the AI learning from the data in those adaptive designs, right? It sees a result and it updates the plan.
It optimizes the path to the peak.
Right. But here's the question. Is the AI actually learning biology, or is it just learning the topology of the data?
That is a profound distinction.
Because if the AI is just chasing numbers, it might find the peak, sure, but it will never understand why the yeast prefers pH 6 over pH 5.
It's a correlation machine. That's what it is. It doesn't know what a cell is. It doesn't know about enzymes or metabolic pathways. It just sees inputs and outputs.
Exactly. So as we lean more on these powerful tools, are we training AI to understand biology, or are we just training it to play a very sophisticated video game with our data? And if we stop asking why, because the AI is so good at giving us the what, do we lose something fundamental as scientists?
That is the danger of the black box. If we stop exploring the mechanism because the optimization is just so efficient, we might get great products, but we might stop advancing the actual science.
Something to mull over next time you're staring at a CSV file generated by a neural network. That's it for this deep dive into experimental design. Thanks for listening and happy experimenting.
And keep asking why.
Hi there, thank you for staying with me until the very end. If these technical insights help bridge the gap in your own process, please hit subscribe and make sure to hit the notification bell. Stay connected for our next deep dive into the realities of biomanufacturing. I am Prasad Ernala. Thanks for listening.